So, continuing our discussion on design for reliability, let me discuss in this session the probability distributions in modeling reliability. We have already referred to exponential density function. So, that is one particular case. We have referred to a particular situation where the exponential distribution is valid, and that is basically during the useful life of a product if you want to model its reliability. So, obviously assumptions are related to exponential density functions. These assumptions are valid. Now, there could be other cases, other types of probability distributions that also you are required to assume while you modeling reliability. Now, while you try to refer to this the modeling, now let me first highlight one particular type of probability of failure, that is posterior probability of failure. Posterior probability of failure. That means this is the probability of AB provided that there is a probability of B. Is it okay? So, this many a time you need to calculate this posterior probability of failure. Is it okay? That means this is Ft versus T. Is it okay? So, this is 1 minus Pb, and this function is lambda e to the power minus lambda t. Is it okay? So, during this time period, that is t, small t, that means up to capital T and then up to capital T plus small t. So, this time period is the small t. So, this part is the probability of the B, and this is 1 minus B. Is it okay? So, this is the representation. It is very simple. So, you can immediately you can calculate this one. So, a posterior failure probability, that is QCT, is defined as the probability of failure. We have used this notation. Okay. How it is defined? It is defined as the probability of failure during T given survival up to T. So, I think it is clear. Is it okay? So, that is the probability of failure. So, this is probability A and B, that means A union B divided by probability B. Probability that A union B divided by probability of B. So, now what will be this expression? That means e to the power minus lambda t minus e to the power minus capital T plus small t divided by e to the power minus lambda t. Is it okay? That means 1 minus e to the power minus lambda t. Is it all right? So, so you come across such terms, and this way you define it. Is it okay? This is the expressions for posterior probability of failure. Now, this posterior probability of failure is independent of the prior operating time t. Is it okay? So, that is the assumptions we are making, and depends only on the duration t of the time interval. Is it okay? That means it is almost what has happened up to capital T time period, that you do not bother. Is it okay? We are assuming that this failure is dependent on the function of the functioning of the product during the small t time period only, this time period interval. If you refer to this figure, you will always you say that this time period we will be bothering about. That means something has happened. Is it okay? Might happen during this time t period small t, and to what extent it might affect the performance of the product. Is it okay? So, the component does not degrade in quality with the time of operation. Is it okay? So, the degrading is very, very important, in fact. That may be the inherent property of the material. So, the product has as a material. Is it okay? Not only one type of material, there could be different types of materials. Now, depending on the physical property. Okay. So, there could be, you may assume that the product may degrade or the product may not degrade. Is it okay? But here that we are assuming that the material property remains same, and only because of the design related factors or environmental related factors, there could be deterioration in the performance of the product. And if there is a deterioration in the performance of the product, is it okay? Obviously, it has got a very close relationship, okay, significant relationship with the reliability of the product. Now, we note here that is a priori failure probability of the component, which is the probability of failure between 0 and t is this, that already mentioned. That means Qt is equals to 1 minus e to the power lambda t. Now, hence for the exponential distribution, right, Qt is equals to 1 minus e to the power minus lambda t. The probability of failure depends only on the duration of time considered and not on previous history. It's clear? So, this I repeat again, the probability of failure depends only on the duration of time considered. Is it okay? That is the basic assumptions, and not on previous history. In other words, the exponential distribution is a memoryless distribution. Is it okay? Memoryless distribution. This point is to be noted. So, if lambda t is substantially less than 1, what you find that the Qt is nothing but is approximately lambda into t. Is it okay? Is almost is lambda into t, and similarly, so obviously the reliability function will be 1 minus lambda t. It's clear? And if lambda is not constant, we can always find QCT as this one. This is the general formulation. That means, on the numerator you have integration t to t plus small t f xi d xi divided by t to infinity, right, f xi d xi. Is it okay? So, this is this way we get the expression when we say that lambda is not constant. Is it clear? So, so this way you proceed, and what is the expected value and the standard deviation? So, we use this is the standard procedure. So, expected value is obtained from mu equals to 0 to infinity t lambda e to the power lambda t, that means t f t dt. T f t dt. So, what is f t? Lambda e to the power minus lambda t. So, obviously, if you simplify, it becomes integration 0 to infinity t, there will be dt, in fact, t dt minus e to the power minus lambda t. Is it okay? And integrating, we get ultimately that mu is nothing but 1 upon lambda. Is it okay? So, mu is 1 upon lambda. So, lambda is the parameter, and so that is 1. And if you want to calculate the variance, and the positive square root of the variance is essentially the standard deviation. So, what do you do? For the case of a failure density function, it's called mean time to failure, that is mean time to failure. Is it okay? The variance is given by variance t, that is sigma square, then e to the t square minus e t whole square. Is it okay? Right. So, this is expected value of t square. We have simplified these expressions, okay, t square lambda e to the power minus lambda t. Is it okay? And then you simplify this expression, integration by parts, so you get 2 upon lambda square. Okay. So, follow these steps one by one, and I am sure that you will be able to follow these steps, and you get these expressions of expected value of t square, that is 2 upon lambda square. And then how do you get? We get the expression of sigma square, that is 2 upon lambda square minus 1 upon lambda square, that is 1 upon lambda square. That means, for the exponential distribution, the standard deviation is also given by 1 upon lambda. Is it okay? So, this is a single parameter distribution, right. So, for components with exponentially distributed failure times, the MTTF is equal to the reciprocal of the failure rate. That means MTTF is nothing but 1 upon lambda. Is it okay? Lambda is the failure rate. So 1 upon lambda is obviously the mean time to failure. It is possible for the MTTF to be greater than the useful lifetime of the component. Is it okay? That is a very important observation in many cases. Is it okay? You have pre-specified the useful life. Is it okay? So that is the second phase in the life cycle curve or bathtub curve. Is it okay? So it may so happen that MTTF is greater than the useful, the lifetime of the component. The failure rate is equal to the reciprocals of the MTTF. So now I have already referred to another term called MTBF. Now let me elaborate on this. For repairable components, we say, I have mentioned also that whenever the failure occurs, what do? You respond to the failure with repairing, and under certain condition, so that you check whether repair is possible or not. Is it okay? So if the product is a new one, in majority of the cases, in all likelihood that the even if there is a failure, so it is possible to be repaired. But as the component ages, now it ceases to be, it may cease to be a repairable say component or repairable product. So what we are saying, for repairable components, the term MTBF is used to indicate the mean time between failures. Is it okay? That means as soon as the failure occurs, then you start repairing. So you go for repair. Okay, you take a repair time, and repair time is also a random variable in majority of the cases. Is it okay? But essentially, you will be doing maintenance work, and maintenance work in majority of the cases, at least 50 to 60% of the cases, or in certain situations maybe 95% of the cases or 100% of the cases, it's absolutely human labor or the manual one. So if it is manual one, in all likelihood, it will be a random variable. That means repair time is a random variable. So how do you define MTTF? Cycle time between failures. Is it okay? And mean time to failure, mean time to repair. Obviously, when you consider the cycle time, that means you start, then after some time it fails, then you repair, and again you get back to your initial state of health. Again you start working. Is it okay? So so there will be in the cycle time both the time to failure as well as time to repair. So when you consider several cycle times, okay, obviously you can calculate the mean time to failure, and you will have mean time to failure plus mean time to repair. So MTTF plus MTTR, mean time to repair. If MTTR is less than MTTF, then MTBF is almost equals to MTTF. Are you getting my point? That means what we are telling you, that MTBF is equals to MTTF plus MTTR. Now supposing this repair time is almost negligible, is it okay? It's very less. Is it okay? Then what you can say, that means approaching 0. So you might say that MTBF is nothing but MTTF. But if suppose this repair time is substantial, obviously MTBF is greater than MTTF. Is it clear? If a failed component is replaced by a new component and the replacement time is almost is very less and it is controllable, then MTBF equals to MTTF plus mean time to install a replacement. So that means the replacement of a part, not the entire systems or entire the product. Then it is not called maintenance, it is called basically the replacement. So at certain point in time, when the component or the system or the product has sufficiently aged, what you try to do, that means the maintenance may not be effective, and in that sense the maintenance may not be economic. So you have to take a decision for replacement. And related to replacement, obviously there could be many approaches, there are many models. Is it okay? So So we are not focusing on replacement, we are focusing on the maintenance part. So the mean time to install a replacement is equals to this one. So if MTT1 is less than equals to MTTF, then obviously MTBF is approximately equal to MTTF. So you know what is MTTF, you know what is MTBF, how MTBF is related to MTTF, and what is MTTR, and then under what conditions is it okay, whether the condition of replacement or the condition of repair, MTBF may be equated with MTTF. But if it is under what conditions, you cannot say that MTBF is equals to MTBF. So all these conditions you must know, and accordingly you assume that whether I need to calculate MTBF and that is enough, or along with the MTTF, okay, I also have to calculate MTBF. Is it okay? So variability of failure time increases with increasing reliability. Failure time increases. Variability of failure time increases. Is it okay? With increasing reliability. That means the variability will be more, okay, in the failure time. Is it okay? The variations. So expected value, and the continuing our discussions on expected value and the standard deviations. So reliability that it will last for MTTF is equals to e to the power minus MTTF. Is it okay? So this is say 0.368. For a given reliability R, the design life of a component or the systems can be obtained from the inverse of the reliability function. That means this is just an example, 0.368. This sort of data I will get. So reliability that the component will last up to TR is it equals to minus lambda t into R. So it is R. So TR is minus ln R by lambda. Is it okay? So this is the expression. So the median of the distributions for R equals to 0.5, that is T medium. So you have these expressions. Is it okay? Minus 1 upon lambda natural logarithm of 0.5. So that is this value. That means 0.69315 into MTTF. So these sort of expressions you can derive. And so what we conclude, the median is less than the mean. Is it clear? So this is just an example we are trying to do. Then the reliability, the T up to T0 time period. So this is the expressions we have made. That means probability that capital T is greater than T0 plus T, provided T is greater than T0. Is it okay? So these sort of conditions you come across, and ultimately assuming the exponential density functions. So you have these expressions, and similarly you have computed this one RT T equals to 0, like this reliability that T plus T0, okay, of TR divided by RT0. So this is the expression e to the power minus T plus T0 divided by e to the power minus lambda T0. Is it okay? That means the component will last up to T0 time period, and this is the component will last up to T plus T0 time period. Is it okay? So this is the conditional one, already it has lasted. What is the probability that it will further the last, or it will further survive for small t time period? So this way we define, and ultimately we will get that it is e to the power minus lambda t, and that is the reliability function. Is it okay? So the several ways you can derive, and in the process your you get, or you learn, or you understand say the many the functions or the conditions, okay, involved, or say the conditions you must be able to perceive, you must be able to understand while you model the reliability functions. Is it okay? That means from the several practical perspectives you to look into, and accordingly all the the aspects to be incorporated in the modeling approach. Hence the burn-in period T0, burn-in period initially, has no subsequent effect on reliability. So this point is to be noted. Is it okay? That means you have 3 phases. Now the question is whether the first phase is impacting the second phase performance or not, and whether the third phase is dependent on say the second phase or not. So what we are assuming that the burn-in period T0, is it okay, that is the first phase in the life cycle curve, has no subsequent effect on reliability and will not improve the component or the system's reliability. Is it okay? That means it is almost an independent as a phase or independent event. The time to failure depends only on the length of the observed operating time T and not on its current age T0. Is it okay? So this point is to be noted, and you have to prove, like say whether this assumption holds or not. If suppose this assumption doesn't hold, obviously your modeling approach will be different. Okay. So now as I have already mentioned that exponential the distribution is a special case of Weibull distributions. But if you want to so the model all the 3 phases of the life cycle curve, is it okay? Then what you need to do, that means one single distributions you can assume, that is basically the Weibull distributions. Is it okay? So let me just highlight some important features of Weibull distribution. So Weibull distribution is one of the most useful continuous probability distributions in reliability studies. Is it okay? So you need to study the Weibull distribution, and when you assume Weibull distributions, so corresponding the reliability related parameters you must be able to say compute. The distribution can be used to model both increasing and decreasing failure rates. That means it is used to model the burn-in phase as well as the wear out phase. Is it okay? So first phase and the third phase of the life cycle curve. The hazard race function already I have mentioned, that is as per the Weibull distributions is a 3 parameter distributions, that is the gamma, that is basically the location parameter. Then you have the beta, that is in the shape parameters, and the third parameter is alpha, that is the scale parameters. So what is you may assume that the gamma, the location parameter, may be assumed to be 0 when you go for reliability modeling. So you have alpha and beta. So what is lambda t? Lambda t is beta t to the power beta minus 1 divided by alpha to the power beta. So this is a simplified expression where alpha is greater than 0. Is it okay? Beta is also greater than 0 and t is greater than equals to 0. Okay. So the corresponding failure density function is given by this. That means ft is equals to beta t to the power beta minus 1 divided by alpha to the power beta in exponential e to the power minus t upon alpha to the power beta. Is it okay? So these expressions directly you get from the Weibull density function, and assuming that the gamma is equals to is 0. Is it all right? So the reliability function is RT. You follow the same approach and you get an expression that is e to the power minus t upon alpha to the power beta. Is it okay? So the failure distribution function is 1 upon RT, 1 minus this expression e to the power minus t upon alpha to the power beta. Okay. So these are the steps you follow. Now there is a special case, that means the shape parameter, that is beta equals to 1. If beta is equals to 1, the Weibull distribution reduces to the exponential distribution with a constant hazard rate of 1 upon alpha. So lambda t is equals to 1 upon alpha, and ft becomes 1 upon alpha e to the power minus t upon alpha. So what is MTTF? Obviously MTTF will be alpha. Is it okay? So the lambda is changed to 1 upon alpha. Is it okay? So it's constant failure. Special case of beta, beta equals to 2. That means the shape will be changing. If the beta is definitely greater than 0, but up to 1 it is, if beta is equals to 1, you can assume it to be, that means the Weibull transforms to exponential. If beta is equals to 2, the Weibull distribution reduces to the Rayleigh distribution. Is it okay? Right. So, with k equals to 2 upon alpha square, right. When lambda t, so it with beta equals to 2, with beta equals to 1, it becomes exponential distribution. If beta equals to 2, it becomes Rayleigh distribution. When lambda t is equals to this, ft becomes this one. Is it okay? So, this is a special case. In general, a value of less than 1 represents a decreasing hazard rate, greater than 1 represents an increasing hazard rate. Is it okay? And equal to 1 represent a constant hazard rate exponential distribution. That means the beta is very, very important. If beta is equals to say 0.5, that means you can with beta equals to 0.5, you can model say the decreasing hazard rate. That means the burn-in phase you can model. If the beta is greater than say 1, obviously you can model say wear out phase. Okay. So expected value of the Weibull distribution, this we have computed, in fact, like mu is the general notation, expected value of t 0 to infinity t ft dt, and then ft is replaced with this one, which is okay, like say Weibull density function. Okay, that is the Weibull density function. Performing the integration by defining a new variable y equals to t by alpha to the power beta, we get mu equals to, okay, the direct you can do this is the gamma function alpha into gamma function 1 upon beta. So, this is the expression, that means mean one, where gamma function is the gamma function is given by, as you already know, that gamma x is nothing but, it's just you recapitulate 0 to infinity to the power x minus 1 e to the power minus t dt with x greater than 0. Is it okay? So, that way we define the gamma function. So, just to remember that this mu value is alpha into gamma function of 1 plus 1 upon beta. Is it okay? Beta we have already defined. So, the following relationships applies for integer values of x and n, like gamma x is x minus 1. So, these are the just the references. As a references, I have given these expressions related to the gamma functions. So, just you go through them. Okay. So, and then you say that the variance of the Weibull distribution is the sigma square, and again you apply this the general expressions like 0 to infinity t square ft dt minus mu square. Is it okay? So, ultimately the sigma square is alpha square gamma 1 plus 2 upon beta gamma function minus the gamma function 1 plus 1 upon beta. Is it okay? So, functions. So, the conditional or the a posteriori probability of failure QCT, again we have already explained. So, this expression you will be getting. Is it okay? So, I suggest that as a part of exercise you derive these expressions. Is it okay? So, you will have better understanding. So, later on we will give you several kinds of exercises on this. So, under different situations, like we have these 4 figures. So, this is with respect to say the hazard function, that is figure A. Figure B is a failure density function. This is the failure density function. Is it okay? And the figure C related to the reliability function. Is it okay? And the failure distribution functions, that is figure D. So, please study all these figures, and you will find that as the value of beta changes, the shape of a particular curve, is it okay, also changes. So, what you need to do, that means you need to know the reasons. Is it okay? Like here, first one is the hazard function, that means the failure rate function. This changes when beta. So, the beta equals to 2, beta equals to 3, and so say beta is equals to 1. So, it is changing. Similarly, this is fx versus x. Is it okay? So, ft versus t. So, this is the shape, right, and this is as it is changing. That means for a certain value of beta, that means the distribution is almost looks like a normal distribution. Is it okay? like Rayleigh distributions we have assumed, right? So when beta is equals to 2, so that is referred to as the Rayleigh distribution. Similarly, we are bothering about the reliability function. So over the time period, how the value of the reliability, the value changes, so that you should be aware of. And alternative or as alternative to reliability, that means it is say the failure distribution functions. Okay, so this is just will be the reverse, right? So these are the obvious. This sort of analysis you do. So RT function is this one. The design life is given by this, and when R equals to 0.99, T at 0.99 is referred to as the B1 life. That is the time at which 1% of the population will have failed, and similarly T 0.99 is called B1 life, the time when 0.1% of the population will may have failed. Is it okay? So this is the Weibull shape parameters. So you refer to this table. I have already explained all these details. So please refer to this table, and then here is an example. Okay, so these examples we may refer to later on, right? So this is the typical examples, in fact, like say a mechanical system has demonstrated a Weibull failure pattern with a shape parameter of 1.4 and a scalp parameter of 500 days. Determine the reliability, that it will last for 150 days, the B1 life, MTTF, the standard deviation, the medium time and the mode time. Is it okay? And the design life for a reliability of 0.95. So this is a typical problem. These are sort of examples you go through, and later on we'll discuss several kinds of numerical problems related to design of reliability. Okay, so I conclude this session.